Hi everyone, this is Xavier Gillard from UC Louvain in Belgium. In this video, I will tell you about my work on DDO, a generic and efficient framework for MDD-based optimization. This talk is built around three parts. First, I will give you just enough background on MDD-based optimization so as to obviate what DDO has to offer. Then, I will give you a few key facts that might motivate you to adopt DDO for your work. Finally, I will walk you through the implementation of a complete solver for an abstract problem. But first thing first, what is MDD-based optimization? Basically, that is any technique where decision diagrams are used to solve combinatorial optimization problems. More specifically, DDO adopts the Branchbound MDD paradigm, which has been recently proposed. Concretely, this paradigm starts from a dynamic programming model of the problem you want to solve. Devising such a DP model should be fairly natural for most computer scientists. Indeed, dynamic programming is at the heart of many classic algorithms such as Dijkstra or Bergman. Still, there is one key difference to the usual approach. Rather than considering the DP model in terms of recursion, the Branchbound MDD envisions it as a label transition system, which one lends itself to the compilation of an MDD. Having such an MDD to encode our optimization problem is nice, as it reduces the maximization aspect of our problem to finding a longest path in a directed acyclic graph, which is pretty easy. However, there's one major flaw in this approach. The compilation of the MDD might require an exponential amount of time and memory. This is where the Branchbound kicks in. Rather than compiling one huge MDD, which would take ages, we will use a succession of small, inexact but bounded size MDDs, which ones are in turn used to either derive an upper bound or a lower bound on the problem. There are two kinds of such inexact but bounded size MDDs. The first one is called restricted MDD, and it enforces a maximum size to the MDD by simply forgetting to develop some of the nodes which are deemed less interesting. Naturally, this means that some solution will be missing from the resulting MDD. But because the solutions encoded in the restricted MDDs are a proper subset of those encoded in the huge MDD, there is a strong guarantee that the decision made along a longest path in the decision diagram yield a solution whose value is going to be a lower bound on the optimal best solution. The second kind of inexact bounded size MDD is called relaxed MDD, and it serves the purpose of deriving one upper bound on the optimal value. This is achieved by merging together some of the nodes from overly large layers and by relaxing the arcs entering the merged node. This is obviously introduced some non-solution in the MDD, but provided that the relaxation is correct, a longest path will always be as long as the path it stands for in the huge MDD, and as such, it will always provide an upper bound on the optimal value of the problem. In a nutshell, what I wish you remember from my succinct introduction to Branchbound MDD is that it is really about dynamic programming, but with the means to control the memory explosion that might occur in the formulation of some DP models for hard problems. I told you that DDO is a generic framework and that it is efficient. But if it's generic, that means you can reasonably expect that DDO will handle all the Branchbound MDD magic for you, and all you will be left to specify is a DP model and its relaxation. Beyond the generic aspect, I also told you that DDO is efficient, and this is illustrated by this table, which one depicts the runtime it took to solve some instance from the MAX2SAT challenge. The number themselves are of very little interest, but what matters most is that those numbers closely match the results from Bergman et al. When they solve the same instances with their specialized extend implementation, which one has been favorably compared to CPLEX. We now reach the part of the talk which I hope you've all been waiting for. From now on, I will guide you through the implementation of a complete solver for the knapsack problem with DDO. Given that this is an online session, I encourage you to set me on pause, code along, and resume whenever you're ready. For the people who might not know what a knapsack problem is, knapsack is a very common and practical problem where one has a knapsack of fixed size and wants to maximize the amount of the value of the objects fitting in the sack. Mathematically, this is expressed as shown below. You have the items which have a value. Those items also have a weight, and this weight, the sum of these weight may not exceed a given capacity of the sack, otherwise the sack would break, and you will have a choice of deciding whether you take an item I in the sack, yes or no. Okay, we're almost good to go and start coding. Almost, because there's just one prerequisite. DDO is written in Rust, which means you will need to have a compiler and a toolchain installed on your machine to be able to compile the code we're going to write. So if you haven't already done so, I encourage you to go and visit rustling.org and follow the instructions in there. They're pretty detailed, pretty much automated. That's very easy, and that doesn't take much time. The first step to take is obviously to create the project. And to do so, we issue the cargo init comment. Cargo is the build system which is shipped with the Rust toolchain, and it's pretty much like Maven is for Java, except that it's much simpler to use. So yeah, now that we created the project like this, you will see, that cargo created a project for you. And now what you want to do is you want to add a dependency in your cargo.toml file, which is the descriptor of your project. And in the dependency section of this cargo.toml file, you want to add a dependency to DDO and specify the latest value of the library, the latest version of the library. We're now at the heart of a matter, because we will start describing a simple data structure representing the knapsack instance. As you can see, it holds three fields, and these are the three ingredients of the knapsack: a sack with a given capacity, a vector of weight, and a vector of benefits, which exactly correspond to those from our mathematical model. And then we will say that the knapsack structure we just defined implements the DP model of a knapsack problem. And here's how we do it. We implement the problem thread from DDO, and this problem thread is basically an abstract interface provided by DDO, which mandates that you implement some functions. For starters, you must be able to specify how many variables your problem bears on. Also, you need to be able to give the initial value and the initial state of your problem. In the case of the knapsack, the state is no more than the residual capacity of the sack. So given that the sack is empty, initially the capacity is going to be the full capacity of the sack, and the value is going to be 0. Also, you need to be able to tell the domain of each variable. That means that for each variable, you need to be able to tell what values that variable may take in any given state. As you can see, a variable, it is always possible to assign 0 to a variable. That means that it is always possible to leave an item aside from the sack. But if we are to include the item in the sack, the weight of that item must be less than the residual capacity of the sac. So it means it must be less than the state of our sac. The final aspects of specifying a model as a DP model with DDO is to specify the transition and transition cost associated with the DP model. These tell the transition between one state and the next one in the DP model. And here you can see that you have the weights in the decision variable. So the transition really is about subtracting from the residual capacity of the sac the weight of the current item if you decide to add this item in the sac. And similarly, the transition cost function is really about adding the benefit of the item you decide to take if you decide to add it to the sac. If you remember the first part of my talk, you'll know that one must also provide a relaxation to the DP model. And that relaxation is about merging nodes together. So in the code, this materializes this way. We first create an empty data structure, and that structure implements the relaxation thread. And the relaxation comprises two parts. The first one is about merging states. And in the case of the knapsack problem, merging state is as simple as taking the maximum residual value of all the states that are to be merged. And the second part of the relaxation is about relaxing the arcs entering the merged node. And in the case of the knapsack problem, well, there's nothing to do. We can just leave the arcs weights as they are. And now we have a complete solver. Your complete solver is there. So we hard code an instance, a dummy instance for the knapsack problem. We instantiate a relaxation, create an MDD on that basis, and then instantiate a sequential solver with that MDD. On that solver, we may call maximize and get the optimum value for the knapsack problem instance which is defined, and afterwards we can even print that solution that leads to that optimal value. That's it. If you now compile your code and run it on your machine, you will happily see something similar to that, and you will be able to verify that the solution you found actually is the optimal and the best you could find for the instance you specify. This is a toy problem, but you can do some very advanced stuff with DDO. And we will now move beyond the basics because this may be quite nice, but DDO offers much more than what I just shown. For instance, it only takes one line to replace the creation of the sequential solver by a parallel solver. This shouldn't have your solver use all of the available hardware of your machine to complete its task as fast as it can. So that's really just one line. Also, you may customize the way your MDD behaves. You may decide to specify a fixed width for your MDD, like so on line 53, where you just specify fixed width for the creation of the MDD. But you might decide to use something more dynamic, like shown here, where you say that a layer may be 5 times larger than the number of assigned variable than the number of not assigned variables. And there are many more options, but unfortunately I will not have the time to cover them all in this 15 minutes talk. So if you have any questions or wish to have more examples or more documentation about DDO, please go and visit our website. It's on GitHub. The code is free, like in Beer, but also like in free speech, so feel free to download it, give a look at the examples, give it a look, and start using it for more than just fun.